Swayam Prabha. Digital India. Educated India.
As per the majority, this is a democratic country. So we start with the most popular choice, which is learning something new, which is Cuda C. So in Cuda C, as I said, there are different ways in which you can make use of Cuda. Library is the most easiest one. We saw some example of how to use CU BLAS and all. Then we went towards the directive-based programming, and now we are looking at the language side of it, for which I need to understand the GPU architecture, right? So the language that we have chosen for this particular session is Cuda C. We had few people who were asking about MATLAB and all. So it's supported in C, C++, Python, Java, MATLAB, Mathematica, Julia, and which other language is getting more popular, Rust. All those guys basically support GPU computing in one way or the other, right? Like in Python, you can code using Numba, you can code using PyCuda. So there are different ways within that language also in which you can make use of GPUs by exposing Cuda. So as I said, Cuda is an architecture. It has different aspects to it. One is the ISA itself, instruction set. Above that, you have your memory model, you have your programming model. So there are different aspects to it which gets attached, right? So in this session, we are going to look at Cuda C, C++, and this will be a starter for you with respect to Hello World, right? And you would be surprised to see that whatever you learnt in OpenACC, almost same thing applies here. It's just that you are just learning a new syntax, okay? The concepts remain the same. So you will learn about Hello World. You will write and execute a C code on the GPU, manage the GPU memory, and then manage communication and synchronization. So these are few aspects which we'll learn. So the prerequisite is fine. I think all of us are basically have been working in this right now. So there are few concepts which we are going to cover. Surprisingly, before OpenACC came, Cuda was the one who had actually given all these concepts. Heterogeneous computing, blocks, threads, indexing, shared memory, sync threads and all. We'll cover these aspects during this session. And then whatever is there, I'm going to post this PDF into the Slack channel. You will follow this and you will write this code on the GPU cluster given to you, right? So you don't need to, after I finish this theory, you can just go ahead and finish that vector addition code. This will give you a confidence that now you can start writing code in another way on the GPU, right? So Cuda programming model says that there are two kinds of devices, there are two kinds of architectures. One is host, another is device. Same thing in OpenACC. Now you will be able to relate it very, very easily, right? So your host is primarily your CPU, it has its own memory, your device, GPU, and it has its own memory. Correct? Heterogeneous computing, Cuda, and if you can see, there is some part which runs on the device, some part runs on this host code. So there is a parallel function which runs on device, serial function keeps on continuing executing on the host, right? So in Cuda programming model, there are three-step process, and that's what you saw in the second lab of OpenACC as well, which is your data clauses, right? So the first step in any Cuda programming is that whatever is the memory that you would like to work on in a kernel in GPU, it needs to be copied from the CPU memory to the GPU memory. That's your first step. Second step is you run things in parallel, right? So if you see, the first step in OpenACC was copy in, correct? So now you are going to execute in parallel on the GPU, which is hash pragma ACC parallel or kernel, right? That's your second step. Third step is after you are done with that work, you will like to use it on the CPU for some purpose, like say maybe printing out the values or storing it in a file or whatever you want to work on, you copy back the data from the GPU to the CPU. So it's a 3-step process. Same concept again. So now let's start with a hello world program. So if you see, this is a typical C program. It has nothing unique about it. It's a hello world C program, int main, printf statement is there. And if you see how are we compiling this code, now we have changed our compiler. Our previous compiler was PGI. Now this is a different compiler which is provided by NVIDIA. It's called as NVCC, NVIDIA C compiler. And you are compiling this code with NVCC. Note the extension of this particular file is .cu. Okay? What is the extension of C files? .c. What is the extension of C++ files? CPP. What is the extension of Python files? .py, right? So, CUDA code is stored, whatever GPU code that needs to be written, it needs to be written in a .cu file. NVCC understands .cu files. Once you do that, it's .a.out and you will compile it and you can run the code and it will print out hello world for you, right? So, there are two things which you will note here. The first thing is, it is still not a GPU code. It is a CPU code. But the CUDA compiler, NVCC compiler is able to compile it and run. But where will it run? On the CPU. There is no GPU code yet. It's a sequential code right now. Next step, I have added additional function to it, which is called as myKernel. Okay? Now this myKernel is a function which is getting called from your main function, right? There are two additional syntax there. Okay? First syntax is __ global __. Second syntax is, if you see how am I calling it? Triple angle brackets. So there is triple angle brackets. What is this triple angle brackets? And what is this global function is something that we'll see. If we didn't have this __ global _ keyword, it is a normal CPU function. It runs on the CPU. As soon as you add __ global __, this is a function which runs on the GPU, right? So it's not that you are learning a new language, you just have appended that function that you want to run on the GPU with this additional keyword. And if you were not to use that triple angle brackets, it will be a call to a normal CPU function, right? If I add that triple angle brackets, it becomes a call to a GPU function. That's it, right? So I'm not learning a new language. What I'm saying is I want to declare this function runs on the GPU. How do you do that in the OpenACC? You call it as hash pragma ACC parallel loop. Here you are declaring it as __ global something. And that triple angle brackets is the one which tells to the compiler this is a call to a GPU function and not a CPU function. Now what is that 1,1? Any guesses? The number of threads, right? The number of blocks or the number of gangs as well as the number of vector and workers that you were talking about, right? That is what defines how many threads you are going to launch finally, right? So as I said, that __ global, this keyword basically says that this runs on the device and it is called from the host, from the CPU, right? CPU main function is calling it, correct? So, and NVCC separates this source code, which means as soon as it sees that it's a __ global function, it extracts that code from your existing source code and creates a GPU binary for it, okay, GPU call for it. Internally it is taken care by the NVCC. What happens to your CPU code? It is exactly remains the same as it was, and NVCC does not do any change to your CPU code, which means NVCC internally will call your host compiler. Like on the Ubuntu or any Linux system, it will call GCC. On the Windows system, it will call Microsoft compiler, right? So your CPU code still is compiled by your host compiler, while your GPU code is the only one which is extracted out by your NVCC and then compiled for the GPU. Got it? Right? So your host code does not change at all. It's just that in between you have taken out that code and you're going to run it on the GPU. And as I said, triple angle brackets is also called as a kernel launch, because in a CUDA world, unlike your operating system, in operating system also you call it as kernel, but here the function which runs on GPU is also called as a kernel. In the CUDA terminology, the function which runs on the GPU is called as a kernel. So if you see, triple angle brackets is basically a call to a kernel, and will return to this parameter of 1, 1. Currently it is a sequential code because you are launching only one thread. Okay, so as soon as you run it, basically it's the same thing. It will just compile with NVCC and it will still print out hello world, because we have done nothing inside the GPU function yet, right? So let us do something. Now run something on the GPU. So you have two vectors. You are going to add two vectors and store it in the third one. Very simple example. So I will change my function now and add that logic there. So what I am doing is I am passing now 3 pointers A, B and C, and then I am adding A and B and storing that value into C. Okay. So there are two things. So as I said, this is a new function called as add. This will run on the GPU and it will be called from the host. Okay. So these are the things, but additionally that you have to see is that we are passing what? Pointers. Okay. Why pointers, and where should it point to? Should it point to the host memory or the device memory? You should always point to the device memory, because GPU will not be able to take the host memory pointer unless you have used managed memory, which we have already talked about some time back. Managed memory also works in the CUDA world. So even if you pass the host pointer, it will work. Currently consider that there is no managed memory and you are going to do it manually. So first thing is you are using pointers, and we need to allocate that memory on the GPU. How do you allocate memory on the CPU? What are the APIs that you use? Malloc and new, right? So what is it in the GPU side of it? We'll see. So device pointer points to the GPU memory, host pointer will point to the CPU memory. Like you have malloc in CPU, you have CUDA malloc on GPU. So if you wanted to allocate memory on the GPU, you will say CUDA malloc. Like you have free on the CPU, you have CUDA free on the GPU. Like you have memcopy in the CPU between CPU pointers, you have CUDA memcopy to transfer data between CPU and GPU to CPU, right? So these are three additional keywords or APIs that you need to use to allocate memory. How was this happening in your OpenACC world? Copy in, copy out, create, right? All this was actually generating this code behind the scenes for you, right? Just by adding a pragma, right? So now let's look at the main function. In the main function now, as you can see, currently I am just adding one value. It's still not a vector, by the way. You can see it's just int A, B and C. Okay. Along with that, we have additional pointers which are D underscore A, D underscore B, D underscore C. A, B and C reside in host. D underscore A, D underscore B and D underscore C are pointers which point to GPU memory. How are you allocating the memory? As you can see, you are allocating memory using CUDA malloc. So you can see CUDA malloc basically takes the pointer which is D underscore A, and then you have to also tell it the size. Currently the size is only 1. So I am just adding 1 values. Even though it is just one value, we are still having a pointer. This is very important, that GPU will only take a pointer in case you want to do some changes and bring it back to the CPU. So if you can see A equal to 2 and B equal to 7, I am just initializing it right now. And then what was the first step? CUDA memcopy. I need to transfer from where to where? Host to device. So if you see, my first parameter is my destination, the second parameter is my source. So I am copying from host to device. My host is A, my device is D underscore A. And if you see here, it says CUDA memcopy host to device, right? So you have done this, and in Pragma world you had done it using copy ins, right? and then you are launching it, and then after my parallel execution has happened, what do? Copy back the data from device to host. And if you see here, it has reversed. It is now device to host. It's not host to device, it is device to host, and you are copying reverse, right? This is your source and this is your destination. Understood? Right? Any questions on this? Is it clear? So as soon as you run this, it will start running your code on the GPU. Any questions? You are able to relate from OpenACC to Cuda. Once you learn OpenACC, Cuda C also becomes simpler actually, because you just have to, once you have understood the concept, now you are just trying to use a different syntax and just trying to use it. And the same will apply for any language, whether it is MATLAB, whether it is Python, no matter which language you talk, is the same. You will allocate a GPU memory, you will transfer it, you will write vectorization code, and then the output will be transferred back. Same code applies. After that, it is all about thinking parallel and profiling and seeing how you can get the best performance out of it. Now, let's do something different, because parallelism is not about one element addition. We need to add many elements in parallel. So let's change my call from 1, 1 to n, 1. That means how many total things I will launch in parallel? N. So I am basically going to launch something called as n number of blocks in parallel. Those blocks will run in parallel. Okay? Understood? It is equal to the number of gangs in OpenACC, right? So as soon as I make this as n, it is going to have that many gangs in OpenACC, right? And second thing is, now you need to start making use of indexes. How does each and every thread know that I have to work a particular element? Suppose if you had a for loop, let's take an example here in the sheet. Maybe that will give you an example. So if I say for I equal to 0, I is less than n, which is the number of elements, I plus plus, right? So if I wanted to add a of I equal to b of I plus c of I, what is this I? It's an index, right? Suppose I launch 4 threads, 1, 2, 3, 4. Thread 0 should work on 0, thread 1 should work on 1, thread this guy should work on second element, this guy. Suppose n was defined as 4, right? So 0 should do a of 0 equal to b of 0 plus c of 0. This should do a of 1 equal to b of 1 plus c of 1. Correct? And same thing like this. So how do every thread know which element to work on? How does in MPI world you are referring to what to work on? How should I divide? Using either thread ID or process ID. So similarly, in the GPU world, you will get an ID assigned to you when you launch. So what you are doing basically is, you are removing this for loop completely, right? You are removing this for loop and you are basically launching these threads, and every thread will get its ID who is going to independently work. That's what you are doing, right? So what is that ID? It's basically that index is given to you by default. Every block will get its own index. How do you define that index? It's block IDX. IDX stands for index. Block IDX dot x. So block 0 will be having an index of 0. Block 1 will have an index of 1. Why is it dot x? Any guesses? In Cuda, you can launch threads in 1 dimension, 2 dimension and 3 dimensions. Any guesses when you will launch 2 dimension threads? Imaging. Image is basically a 2-dimensional space. So you can launch threads in x and y direction. Any example of 3-dimensional space? Video, right? or in a healthcare world, MRI reconstruction image across time, right? All these kinds are examples. So you can launch threads in X, Y, and Z direction. Right now, let us restrict it to dot X only. So every block will get its own index. So what does it mean is, if I was launching 4 blocks, every block will work on different elements in parallel. Okay? So that's what it does. So let's look at our main function now. So now in this example, now I have defined n as 512. So we are going to work on 512 elements. And then if you see now, CPU has also become pointer, because now you need to allocate on CPU as well. It's not individual element. So you are allocating memory on CPU. Your GPU code remains the same. There is no change here. And the only change now is that instead of using ampersand a and all, you are using a because it's already a pointer, and you have made it as n comma 1. Okay? So the same code will run and will start giving you the same results for 512 elements. It will launch 512 blocks in parallel and give you the results in parallel. So what we have learned so far, we have seen CPU, GPU, we have learned what a global function is. We have also seen how to pass the parameters to the GPU. We have seen 3 functions, malloc, memcopy, and free. And then we understood how do you launch parallel blocks on the GPU. But now you might ask, what is this comma 1? For which, let's move towards something called as threads. Okay? So instead of block, let us launch multiple threads. So instead of block IDX, now if you see, you have thread IDX. And instead of doing it as 1 comma n comma 1, you are doing 1 comma n. Do you see that? Right? So there are 2 changes which we are doing. The first one is, instead of block index, I am using the thread index, and I am having, instead of n comma 1, I am saying 1 comma n. So how many blocks are getting executed? One block having how many threads? N number of threads. The same thing happening, but instead of multiple blocks, now you are launching multiple threads here. And the same thing will run as it is. Okay? And it will give you the right result. Same thing, same code will run, and it will give you the right result. And that's what is thread level parallelism in GPU. But why are we not combining blocks and threads? In the real world, you will actually not have n comma 1 or 1 comma n, you will have m comma n. That means you are going to launch m number of blocks, each having n number of threads. It's not very simple like CPU, because if you look at the GPU hardware, it has 2 levels of parallelism. You first define the number of threads within a block, and then you will say how many blocks you are going to launch. It's a 2 level of parallelism as compared to a single level of parallelism. So this is an example. Let's launch now multiple blocks, each having multiple threads. But how does the indexing work? Right? So this is an example where you have total how many elements to work on? 32 elements. And in this example, I have decided that my number of blocks are how many? 4 blocks, each having how many threads? Sorry? 8 threads. Correct? So if you see, my thread ID ranges for every block from 0 to 7. 0 to 7, 0 to 7, 0 to 7. And what is my block ID? 0, 1, 2, 3. Okay? So how do I find the index now? What will be my formula is kind of already given below. If you can see, it is actually block IDX star m plus thread IDX. But let me give you another example to simplify it for you so that you understand what I am trying to tell. So suppose if you had a double dimensional matrix, right? So 0, 1, 2, 0, 1, 2. If I were to do a single dimensional part of it, if I were to convert it to a single dimension, it will be 0, 1, 2, 3, 4, 5, 6, 7, 8. Right? So 0, 1, 2, 3, 4, 5, 6, 7, and 8. Okay? Are you getting this? Converting from a 2 dimension to 1 dimension values. What is the formula if I had a for loop for y equal to 0, y is less than rows, y plus plus, and then I have the next loop which is for x equal to 0, x is less than the number of columns, x plus plus. What is my formula that for which I am going to use to have a single dimension here? What is the formula? Sorry? Y into number of columns plus x, correct? Let's test it out. What is the y here for phi? What is y? 1. How many columns are there? 3, right? 1, 2, 3. And then what is the x value? 0, 1, 2. So what is the value? That's how you do it, right? Correct, na? So now relate it to this one. It's almost the same. Try to relate it. So what you are doing is you are multiplying your block ID by the block dimension plus your current thread ID. It's the same. There is nothing new. It is quite simple there, right? So let's take an example, the same example. My block ID there is 2. I am multiplying it by the block dimension which is 8 elements. So you multiply by 8 and my current thread ID is 5. It will give you 21, right? Same thing. There is no change at all. It's the same concept. I just showed it to you in a different way because you are able to relate it better. So now instead of just using block ID and thread ID, now you are multiplying it, and you can see now I have added one more variable here which is called as block dim. Block dim will give you the dimension. You don't have to pass it. It will already give you the dimension. So you will be able to calculate that index as well. So now this is a real code where you are multiplying 2048 by 2048, so many elements. Addition you are going to do it in parallel. The first thing that you have to do is to define the number of threads per block. That's your first thing. How many threads do you want per block? You remember I told even in OpenACC, you're going to play around with vector size, right? Similarly here, you are going to first decide the number of threads per block. You can have 32, you can have 64, you can have 128, you can have 512, you can have 1024 as well, right? There is a maximum limit. It changes from hardware to hardware. The latest hardware allows you 1024 threads maximum per block. And you can have more number of blocks like this, right? But the recommendation is it should be always a multiple of 32. That is something which Cuda basically internally launches the threads in. It's a multiple of 32. So you should try to strive to have that number to be a multiple of 32, divisible by 32. Okay? So once you have this number, so let me ask you this question. If I define the number of blocks as 5 and 2, and if my number of elements were this, what will be my number of blocks I will launch? What will be the formula? It's just pure division, n divided by the number of blocks. Now, some of you were asking, can I play with number of grids, the number of gangs and all in the previous session, right? It's very simple calculation actually which can be done. So you just have to do this simple calculation and you can launch and decide the number of gangs in OpenACC as well. But the compiler already does this calculation for you, so you don't need to do it manually. Here, you need to do it manually. So your overall code, if you see, runs fine and it works exactly the way you were expected to do, and it will give you the result. Okay? So you can handle the arbitrary number of sizes as well. Any questions so far? Yeah. Exactly. So that's what I'm coming to the next slide actually. Why do you need threads and blocks? Why can't I just launch threads? It's the same that I explained to you in the OpenACC session as well. Why to bother with both threads and blocks, right? Why can't I just have one? The reason behind that is, in a Cuda programming model, two threads within two different blocks cannot synchronize or talk to each other. Okay? To give you an example, again relating back to the example so that it becomes much more clear to you. You remember the reduction example? So you have 1, 2, 3, 4, 5, 6, 7, 8 elements. So I want to first, I am going to launch some threads which are going to execute this, correct? And then it's going to give me a new value, multiple threads. What is this? Synchronization. Then again you are going to do this. Then again you will synchronize. Then again you will come back. Right? So this is what I mean by talking to each other. So now this block, if this was one block which it had two threads, this thread can synchronize with this thread, but it cannot synchronize with this. Suppose this was block 1, this was block 0, and this is thread 0, this is thread 1, this is thread 0, this is thread 1. It cannot have a global synchronization. It's not allowed for us to have a global synchronization in the CUDA programming model. So in case you want to have that talk to each other, we only allow it within a block. Okay? And this is the reason why we have these two levels, that in case you want to synchronize or you want to talk to each other, you will have to basically have that within a block. You cannot synchronize across. Now it might sound complicated for you, for which I am going to come to the next part of this session after you finish this hands-on of this till this level, which is page number, I believe, 60 something. I don't know what is the page number. So you have to, I'm going to post this into the Slack channel. You're going to start doing hands-on and you have to finish this vector addition code till here. Okay? Questions? Okay. Very interesting question. What does the CPU do when GPU is being launched? And that becomes to the most fundamental question. So all the GPU calls are asynchronous by default. So CPU returns as soon as you launch something on the GPU. Now it is up to the programmer what they would like to do. Now they can do some kind of a parallel processing on the CPU as well if they would like to do. And they can finally call things like CUDA stream synchronize or device synchronize to wait till the time that kernel comes back to synchronize at the CPU level, right? But all the calls to GPU are asynchronous by default. It will come back as soon as you launch it, and then you can do whatever operations you want to do on. Okay, we'll first ask this and then go here.
Sir, inside those global functions which you showed previously, so if there are some statements like printf also, will it throw an error?
No, so printf we have enabled it currently, but it is just for debugging purpose to a small extent. It is not meant to be used, but you cannot do any system calls. You cannot do fread, you cannot do fwrite, you cannot do MPI send, MPI receives, you cannot do any system calls. It will throw an error, compilation error, basically it won't even compile.
So that printf is executed by the GPU.
Yeah, so what we have done is we have created a very simple kernel behind the scene. What it does is, whatever printf, what is the output it comes, it stores it in a buffer and then it pushes it to the CPU behind the scenes, then CPU prints it out. So it's just a mechanism that we have come out just for debugging purpose when people want to debug it, but it's not meant for anything else. No system calls inside. As I said, GPU is a parallel computing hardware. System calls are not like that. So you can't do or use those things. It doesn't run an operating system, if I were to say, right?
Sir, so as you mentioned that the kernel call is asynchronous and further the CPU code, whatever is there, it will run. And regardless of the kernel is completed or not.
Yes.
So now in the OpenACC, we have a for loop which is running in parallel. Before this for loop executes, well, the further CPU code will run or will it wait until
No, so by default in OpenACC, there is an implicit synchronization which gets added. So it will, CPU will wait behind the scene, it adds it and will wait till your loop is added. But you can make OpenACC calls asynchronous by adding a async clause. If you add that, then you can actually use ACC synchronize primitives to synchronize. So by default, it is implicitly synchronized always. That's the default behavior. But if you make it as async, it will go ahead. There also? Okay, so this is another good question. So CUDA memcopy calls are by default synchronous. They are not asynchronous in nature. But we have asynchronous APIs for memcopy as well. They are called as CUDA memcopy async. So in case you want to do that, you can also do async calls to memcopies if you want to. Otherwise, memcopy calls are synchronous in nature. Any more questions?